Hello, good evening, everyone. Can anybody confirm? Am I audible?
Yes, audible.
Thanks. So, we will continue the last session where I was discussing some problem based on synchronous motors and generators. In last session, some questions was also there. So, let me read what was the question. Uh, One question that in Balk it was asked that if synchronous machine is running as reluctance motor, then what will be its speed? Okay. So, synchronous reluctance motor is another type of synchronous machine itself. The difference between conventional synchronous machine and this reluctance motor is that it works on the principle of reluctance, and its speed would be synchronous speed only. So, nothing else than synchronous speed. And let me show you one model of synchronous machine. Okay. So are you guys able to see the model on the screen?
Yes,
So this is nothing but the synchronous reluctance motor. And this axis is known as Q axis and this axis is known as D axis. And in conventional synchronous motor, we have field wound on rotor, but here no coppers are present on the rotor side, and only a stator has the windings. Let me show you the windings as well. So you can see here the stators are only wound and there are no winding on rotor side. And if you see the flux path, so this is how the flux flow in the machine. So just for the demonstration, I thought I should show if I have. So any question in this? Okay, so I hope you got the idea. And it is running pure on synchronous speed, nothing else. You can see as the flux is moving, the rotor is moving at the same speed. So it is similar with RMF. So the speed would be synchronous speed only. So this was question by Nokirti, I guess. So is this clear to you, Nokirti? Yeah, fine. Thanks. So let me go ahead with the problems. So yeah. So here in the problem, it was asked to calculate the ratio of excitation current of machine A to that of machine B. Means we had to calculate the IF1 or IFA divided by IFB. What would be the ratio of these two currents? So to calculate the current, field current, there are no information regarding field voltage or something is given. So, but one information is given that we can assume that the circuit is linear, magnetic circuit to be linear. It means IFA by IFB would be directly proportional to EFA by EFB. What I mean to say by this, if you plot, I think OCC curve it is called, or some other EF versus IF, it is open circuit characteristics, it would be linear. We are not considering this saturation in the problem. So we can consider that it is linear. So whatever the value at, sorry, whatever the value at some EF, IF. So EF A, IF A, EF B, IF B. So this ratio we have to calculate in the problem. Now, uh, two parallel connected, okay, fine. Two parallel connected, and they are supplying 50 MVAR reactive power, right? No real power is supplied to the grid. So 50 MVAR reactive power they are supplying. Means both machine has to be operate at overexcited condition. And to overexcited means it would not be some angle. It would be directly 90-degree. Current would lag by 90-degree. IA1, its angle would be 90-degree lagging. We all know for lagging power factor, when the power factor angle is 90-degree, then only complete reactive power would come in picture. No active power would be there. And that's the question related to. Here, no,
Sir,
yes.
sir, apparent power is equal to reactive power in
Here,
this
yeah,
question according to.
yeah, we can infer from that, right?
Thank you, sir.
Uh, So here, apparent power is equal to the reactive power, as rightly pointed out. So IA2 would also be pi by 2 lagging. So we can say IA1 angle minus pi by 2 and IA2 also angle minus pi by 2. Okay. Now we infer from that statement. Now synchronous reactances are different. So we have to apply the KVL in two parallel circuit. And how those two parallel circuit would be connected, let me draw it for you. So this would be EFA, JXSA, EFB, JXSB, and here grid is connected. So let's say here grid is connected and it is operating at 50 MVAR, and what other statement is there? 50 MVAR, 11 kV. Now this path would have some current IA1 angle minus pi by 2. This path would have also current IA2 angle minus pi by 2. And one more information is there. If you see, sorry, uh, they together supply uh, current supplied by both the machines are equal. So this statement we can use as an equation. So the total current that would be IL. IL is nothing but the IA1 plus IA2. So this is given by the question. Now, and also we can write it as IA1 is equal to IA2 is equal to IL by 2. This we can write. Now, the other thing in the problem is to now we have to just find the uh, EFA and EFB, the ratio of EFA and EFB, and then we can calculate the ratio of IFA and IFB. For that, we have to apply some KVL. We know the voltage is 11 kV at this point. 11 kV is there. Excess A we know, excess B we know. We can calculate EFA. So let us proceed. And if any question in synchronous motor is given with either apparent power, real power, reactive power, doesn't matter. You can calculate the armature current. So that is true for any problem. The apparent power or reactive power is here given, voltage is given. We can calculate current by the formula which is known as IA is equal to MVAR if it is given, fine, root 3 VL sine phi, right? Why sine phi? Because it is reactive power. If it would have been apparent power, then I would not have used this sine phi angle, right? So we can calculate 50 into 10 raised to power 6 divided by root 3 into VL is 11 kV into sine 90 degree. Any doubt why I am writing sine 90 degree? If not, then let us calculate, or I have the calculated value here. So that would come out to be 2624 angle minus 90 degree. So that would be IA, ampere, sorry, IL. We work all IA, IL is same, okay? Because it is, armature current, most of the time it is referred as. Now, if we know IA, we can calculate IA1 is equal to IA2 is equal to 2624 angle 90 divided by 2. That would be 1312.16 angle minus 90 degree. If all the angles are same, then we can add it arithmetically. We need not be worry about the phases here, right? All the currents are in phase. We know now IA1, IA2. We know XS A, XS B. We can calculate EFA. So EFA is equal to VT plus or minus. This is like synchronous motor, and in synchronous motor, VT is higher than EF, right? Because supply will be always higher than the generated voltage. So VT minus J IA XS. I will try to break all the components in phase value. So 11,000 divided by root 3 minus J into IA angle minus 90 into XSA. What is the value of XSA? XSA is 1 ohm and XSB is 3 ohm. So 1 ohm, right? This 90 and this plus 90 would be cancelled. So it would be the arithmetic now, and its value would come out to be 7662.85 volt, right? This is EFA. We calculated EFA, we have to calculate EFB, and that would be same manner IA1 VT minus JIA2 XSB, and again it would be 11,000 by root 3 minus J and IA angle minus 90 into 3, and it would come out to be 10,286.85 volt. We calculated EFA and EFB. Our job is almost done. Now we have to take the ratio of the two values, which is nothing but EFA by EFB, which is 7662.85 divided by 10,286.85, that would come out to be 0.745. It is proportional. Yeah, some questions are there. Yeah, Akhila, you ask, please. Akhila raised his hand, I guess. Okay, so I guess he had not any problem in this question because this is the answer of the problem. So I solved it. Any doubt in this? Okay. If no doubt, then I will move on. And this question was appeared in GATE 2017 for 2 marks. So synchronous machine is very important question. At the same time, it is very easy topic to understand. And problems are just KCL, KVL with phases. So if you guys are good at network basics AC circuit, then this topic would not bother you much. Now, I will take some other problems. So, yeah, so I guess this problem was there. It is again based on synchronous machine. And okay, so we will discuss what is this. I guess I haven't discussed this problem earlier, right? Can anybody confirm? No, because I guess it is a new problem. Anyway, so let us go ahead in this problem. So this problem is saying that a 50 hertz a star connected cylindrical rotor, not salient pole rotor, is running as a motor. So first information, it is a motor. It is very important to find the machine is running as a motor or generator, right? So it is motor. Now 6.6 kV grid means 6.6 kV of supply means terminal voltage of 6.6 kV line. It draws current at unity power factor, just opposite of the last problem. Here it is operating at unity power factor. It means it has nothing to do with reactive power. Now, the synchronous reactance of the motor is 30 ohm per phase. Okay, fine. Load angle is also given. We have to calculate the power delivered to the motor. So what would be the power delivered to the motor? So first of all, we should always keep in the mind the power flow in the motor. So first of all, input electrical power would go to the motor. Electrical losses, what are they? Copper loss, core loss. Yeah, Akhila, you want to ask anything? You are raising your hand quite often. So here, power would be developed and some mechanical loss means rotational and frictional windage, frictional plus windage loss. And here it would be power output. But many a times this rotational and friction and windage loss would not be given. Okay, so you have to ignore that, and many a times power developed would be equal to power output. Okay, just for the simplicity sake, nothing else. So in this problem also, no mechanical losses are given. So this is the circuit of motor from VT, it is input power side to developed power side. From higher angle to lower angle, power is flowing. Okay. Uh, we discussed in the last session that apparent power, if any power we have to calculate, first we should go with apparent power. If we know apparent power, we can calculate any power, either real or reactive. Okay. So I just went ahead with the formula EFIA conjugate. EF is lagging with load angle, that is delta, and IA is uh, angle of current is zero. Why? Because unity power factor is given in the problem. I just substituted all the value in the equation. So uh, I did all the jugglery, mathematical jugglery, and here I reached to the point. So this is the expressions in phasor. And if we break into two components, we will get this component. So cos 90 would be 0, and here cos 90 minus delta would be sine delta. So this is the famous formula of power developed, that is EFPT by XS sine delta. So it can be derived. If you want to remember, I would never recommend to remember anything, but if you want to remember, you can remember that. It is a very famous formula. And most of the numericals of power developed or power output based on this equation. So now, yeah, so in the problem, it was said that mm, power factor is unity. It means no real input power is coming from the supply, right? Because unity power factor means only real power is coming, no reactive power. So that's why this condition I exploited in the problem. And we know if we want to calculate input reactive power, I again went to the conventional expression, that is Vt angle 0, I angle 0 conjugate, VTIA conjugate. So I equated that to uh, in in complex form, and again I broken into two component, and this time I need reactive power, so I will break into sine component. So I multiplied with sine 90 minus sine 90 minus delta. So this would be the expression of input reactive power to the motor. You can derive, right? Any issue till this point? You can derive these two formulae, either input reactive or developed reactive power, or input real power or developed real power. We can derive anything. We just need to know what would be the Vt or voltage, or what would be the current at that stage. Okay. Now, we segregated this equation with Vt by Xs, Vt minus EF cos delta, and we have to equate to 0. So Vt is equal to EF cos delta if I equate it to 0, right? So cos delta come out to be Vt by EF. Okay. And here I wanted to know EF because everything else was given. Vt was given, delta was given. If we know the magnitude of EF, we can calculate power developed from this equation, right? I came here with Vt, Xs, sine delta. We knew all the terms, but EF was not known. So EF, more often it would be related to the reactive power. Okay. So for that sake, I went through the reactive power. Now I calculated EF phase value by putting the phase value of terminal voltage, and this cos delta is cos 30 degree, and I achieved 4400 volt of phase value of excitation EMF. Now to calculate the developed power, we should always remember to multiply it with three factor because it is a three phase. If you do not want to uh, worry about the factor of three, you should take the line value of all the terms. But it is better you break into phase component and you proceed. So here I multiply three times V phase E phase by XS sine delta, and I did that mathematical equation, and I can get 838.3 kilowatt of developed power in the motor. So any issue in this problem or any doubt in the problem? I might have went fast because since last class I am discussing only this topic. So any issue in this? Great, thanks. So I should move ahead now with other problem. Hmm. One last problem based on this synchronous motor and generator. Okay. Uh, this problem appeared in gate 16. If you are not able to see, just tell me in the comment section. So I hope you are able to see the problem. So in the problem, it is asked, although it was for 1 mark only. So it is asked that consider a system consisting of a synchronous generator working at a lagging power factor. Okay. So synchronous generator, lagging power factor. I don't know why my pen is also lagging here. And synchronous motor working at an overexcited condition. Overexcited. What does it refer to overexcited? It indirectly want to say it is working at leading power factor. Okay. If you derive the equation of reactive power, you will get two conditions. Either Q would be greater than 0 or less than 0. If less than 0, it means it is delivering the reactive power for motor. It is not, it is just opposite for the generator. Here generator is operating at lagging power factor. It means it is overexcited. Okay. So they tested your basic concepts of reactive power from this problem. And now a directly grid connected induction generator. Again, induction generator is also. So three machines they tested at once. So induction generator cannot be overexcited because it consumes lot of reactive power. So it would be always underexcited. It can give the other machine real power or active power, but it cannot give any reactive power. So that is the drawback of induction motor, and it would be uh, induction generator. So it would be, yeah, Anubhav, you want to ask something?
Yes, sir.
Please.
Sorry, overexcited means our field generated is more than required.
Yes,
So
yes.
how you know that it is leading power factor for motor?
Huh. So synchronous motor is overexcited, right? When it has more, what to say, more reactive power, means uh, it will have the current. Let me draw the phasor diagram for that.
Sir,
Huh.
sir, uh, for power factor, we use tan inverse Q by P. So as Q increases, the power factor decreases.
Hmm.
So
From huh,
overexcited means more power, more reactive power.
more reactive power. If you recall the V curve or inverted V curve, right? So
Yes,
there,
sir.
if you increase the real power, sorry, reactive power, the first of all, that power factor angle get decreased and then increases, like uh, this type of V curve, if you remember, as IF, and this was cos phi. Okay, so first it would be lag, and then it would lead, right? So this is the case for which motor or generator? Can you tell me?
Motor, sir.
Yeah, correct. So this is for motors. And the inverse of this, if you go this way, this would be for generator. So you have to link in your mind that how you can tackle this type of confusion. You should fix it in your mind that how to link lagging power factor, overexcited, and to the machine, type of machine, right? Lagging power factor. generator, it would be overexcited. If you remember for one or understand for one or fix it for one, it would be easier for the other machine. As of now, since I work on motor, so I keep in my mind a synchronous motor, if it is leading power factor, it would be overexcited. Now, if generator would come, I will just reverse the situation, right? In generator, lagging power factor, overexcited. Leading power factor for generator, it would be underexcited. So anyway, if you want to fix it in your mind, you do that. Okay. So is it fine? Uh,
Yes, sir.
yeah, thanks. So I was talking about induction generator, and it will be under excited always because it has a high, magnetizing inductance compared to all other machines, and it does not have any other supply. Okay, so it would be lagging power factor. You would not see any induction motor operating at leading power factor. Okay. So the problem was regarding consider capacitive wall to be source and inductive wall to be sink. Okay, they tried to confuse more, uh, like inductive wall to be a sink of reactive power or capacitive wall to be a source of reactive power. Like capacitor can deliver the reactive power and inductor will observe absorb the reactive power. Okay. So now, that's why capacitors are sometimes known as condensers, or overexcited synchronous motors are sometimes known as synchronous condensers. So we have to choose which statement is correct. Synchronous motor and synchronous generators are sources, and induction generator is a sink of reactive power. So what do you think about this statement? Uh, is it correct or wrong? Here it is saying we have to identify about the reactive power source and sink. So which one is working as source and which one is working as sink? Source means which has more, sink means which has less. They has to receive, sink has to receive, and source has to deliver. So we saw here synchronous generator is overexcited, so it can deliver, so it can work as a source, right? Synchronous motor is also overexcited here. It can also work as source of reactive power. Induction generator is underexcited, so it will act as a sink of reactive power. So our option A would be correct in this case. Fine. I guess this graph would be inverted. Uh, right? Can anybody correct me? This graph should be inverted V, right?
Yes, sir. Yes, sir.
Uh, sorry for the mistake. Let me move on. Uh, So this was all about synchronous machine till now. Maybe later I may get some other problems, but I think you would have got some idea how to tackle
Sir,
problems. Huh.
sir, I want to discuss more on this curve.
Mhm. Yeah, tell me please.
Sir, if power factor is lagging,
Mhm.
it means the armature terminals has to supply more reactive power
Full motor.
for motor.
Hmm.
Uh, so it will work as overexcited.
Until no, it will work as underexcited. I showed you, no.
If armature supplies more reactive, armature delivers reactive power, then it will work as underexcited for motor.
Uh, no, if motor is working as a lagging power factor, right? So it means it has less reactive power than it required to operate at unity power factor. Yes, let me tell you this way. Let me put it that way that armature and field. These two windings are present in synchronous machine. Field winding job is to provide all the reactive power to synchronous machine. And armature winding job is to provide all the real power to the synchronous machine. Okay. Then this synchronous machine would be at unity power factor, right? Because no reactive power is supplied by the armature. Now, let's say uh, reactive power provided by field winding is less. Okay. Now, armature has to compensate for that. And to compensate, now armature would have two components. One is for real power and one is reactive. It is this reactive part job was to be done by field winding, but it is not able to fulfill his job. So now armature should come in action and it should provide the reactive power to the motor, right? So, but this is taking armature is also taking power from supply or kVA. It is apparent power is taken by armature winding from supply only. Okay, so now we have some lose on power factor. This is Q by P. Okay, so this is Q by P here because some components are going in maintaining the flux in the machine, rated flux in the machine, and the rest of the component is going to maintain the power. So that is the case. And of course, if it is the case, then it is under excited and lagging power factor. You got this point?
It was lagging because armature is also providing reactive power. Am I right?
Yes. Yes, yes, correct.
Okay, thank you.
Thanks. Any doubt in this anymore? If not, then I will move on to some power electronics topic. So, this problem appeared in GATE 2016 and it was for 1 mark. And in the problem, it is said that it is a buck converter. From figure also we can see it is a buck converter. And output voltage and inductor current can be assumed as a ripple free. Okay, so no ripple in output voltage or capacitor voltage or inductor current. Now, VL waveform is also given. This is VL waveform. And assume all devices are ideal. We have to calculate the duty cycle of the buck converter. Okay. So, if it is a continuous conduction mode, we can go ahead, we can calculate Vg minus V naught or whatever, and D is equal to V naught by Vs. But let's say you mark this answer and the converter would come out to be discontinuous conduction mode, then you would lose your marks. So, for that, we should always check once. In GATE, we should always check once just to make sure that whatever you are doing is correct. Okay. Otherwise, what's the benefit in knowing and not getting the correct answer? Okay. So for that purpose, and from this waveform also we can see that inductor voltage is continuous. So it is not becoming zero for any period. So that is the first indication. It would be CCM. If any indication we get, then we should move ahead and we should apply the formula of V naught is equal to dVs. Okay. And I was saying that VL is not equal to zero. It means IL or inductor current would not become zero at any instant in steady state. Okay. So now we know that it is continuous conduction mode. We are not given Vg, we are not given V naught. So we have to know the value of Vg and V naught to calculate the value of duty cycle. So, but we know VL and VL during T on means when this switch would be on. So what would be the value of VL? So when switch is on, what is the value of VL? Can anybody tell me?
But P,
Yes, sorry, I did not get.
30.
That is 30, but what is 30? The in
V in
para
minus V
in
in minus V naught.
Yeah, yeah, correct. In parametric term, I wanted to ask. Thanks. It is correct. V in minus V naught, that is Vg minus V naught. Vg is given here, so I am using the same terminology. Now during off time means this switch is now off. This switch is off. It means the diode would be on. So now VL would be minus V naught if you apply KVL in that. So that I did here, VL is equal to minus V naught, and from waveform you can observe it is minus 20 volt. So V naught come out to be 20 volt. Now we know V naught and Vg minus V naught. We have two equations and one unknown or two unknown. So Vg come out to be 50 volt. We know V naught, we know Vg, so it would be 20 by 50, 0.4 would be the duty cycle. So it was very easy problem, I guess. So any doubt in this problem? Okay, fine. So let me move ahead. Let's see any other problems. I guess. Hmm. One more problem based on rectifier. So these kind of random problems would give you some clarity about the topics. Okay, do not think that these are random. So it is doing your revision in a great way. You should, even if you study, you should revise like randomly. Anytime you pick any topic and just do the revision. So that is the purpose of this type of session. So let me show you the problem. So in this problem, we have to find the current through this diode. Okay. So what will be the value of current through this diode? And it was appeared in gate 17 as well. This problem has two topic covered. One is transformer, one is you know single phase full wave rectifier, and that is nothing but the which topology of single phase rectifier, can anybody tell me which topology of single phase?
Half control.
Yeah, controlled, that is correct. Any more
Fully
hint?
fully controlled.
Half control.
Half
Fully
control,
controlled.
full controlled. Okay. So, any specific name you might have heard or studied for this type of topology? Any specific name? Like here, it can't be fully controlled because, yeah, semi-controlled. Someone said semi-controlled. Sai commented semi-controlled. Correct, semi-controlled. And also it is known as asymmetric converter. So, uh, it is asymmetric. Why asymmetric? Because it has two diodes, and diodes are known as uncontrolled switch, and thyristors are known as controlled switch or semi-controlled switch, because we can control the turn on of thyristor, but we cannot control the turn off of thyristor. That's why we use lot of commutation circuits and all. So that's the thing here. Now let me move this thing. So now in this problem, it is asked to find the conduction period, sorry, RMS value of current through the diode D3. Okay. So now, mm, let's say we will go step by step. Okay. From 0 to 90, 90 to 180 or so on. So from 0 to 90 or pi by 2, which devices would conduct? Anybody?
T1 D2.
T1 D2, ideally it should conduct, but T1 has the triggering angle of 90 degree. So it is sure that T1 would conduct after 90 degree. T1 would not conduct before 90 degree, right? So, and in general scenario, what happens if this both would be thyristors or diode? Let's say diode to make it easy. Huh. So 0 to pi by 2, T1 D2 would have conducted, right? But here T1 has the firing angle of 90 degree, so it cannot conduct. So, I think you are getting confused with that. Okay, so from 90 degree to 180 degree, from 0 to here, it is sure that D2 would conduct for this period, and the other device I don't know at this point. Okay, but after pi by 2 to pi, D2 would conduct, that is for sure. Now T1 would also conduct because it got its firing angle. Okay, and now the circuit is completed from pi by 2 to pi. But I still don't know what happens from 0 to pi by 2. Okay, we will come back to this point. After pi to 3 pi by 2, at pi, D2 job is done. It will go in off state. Now, D1 would come out in action. Anybody had any issue in understanding how I am writing directly? If not, then I can move on. Otherwise, I will explain the basic how anode and cathode thing is working here. Uh, for positive cycle, this is plus and minus. For negative cycle, this is minus and plus. So if you apply the anode cathode rule, you will get that. Okay, fine. Side saying that, please explain. See, if this is sinusoidal source, okay. So if this is sinusoidal source, it would have some positive time, some negative time till pi till 2 pi. Okay. So for pi 0 to pi, this terminal would be in this manner. Okay. And if here it is positive, it means thyristor is acting as forward blocking mode. Or it can also conduct if we give the trigger to the thyristor during this period. So T1 and D1 would be forward bias. How D1? Because, sorry, T1 and D2. How D2? Because D2 cathode is connected to the negative terminal of supply from 0 to pi. So D2 would be in forward bias for 0 to pi. Now, from pi to 2 pi, what will happen? From pi to 2 pi, now the polarity would be reversed. Sorry, polarity would be reversed. So now T1 would be reverse bias and D1 would be forward bias because this negative terminal is connected to the D1. So D1 would be forward bias and positive terminal come across the T2. Okay, T2 and D2 is connected to the uh, cathode of D2 is connected to the positive terminal. So D2 would be off. So D1 and D2 would be forward bias. If diode is forward bias, it would conduct. But if thyristor is forward bias, it is not guaranteed that it will conduct. We have to give the turn on signal to the thyristor. That is known as firing pulse. Okay? Firing signal we give to the thyristor, then it will conduct. So that firing angle is mentioned here 90 degree and 270 degree. Means we are not giving at 0, we are giving at 90 degree and here at 270 degree periodically, right? So is it clear, Sai? thanks. So now I will move ahead and so I discussed till pi by 2 to pi. After pi, what will happen? Pi to 3 pi by 2. T1 was on till pi, but after pi, T1 would only be on if any energy elements will be present in the circuit or in symmetric configuration of semi-converter. If this freewheeling diode is not there and if some inductor is present in the circuit, then during turn on, this was being charged. Okay. Now during turn off, this charged energy would be either discharged through this diode or through this way, D1 and T1 or D1 and T1 only because T1 was on. Okay. So I will explain more about this, but let me write here. So from pi to 3 pi by 2, since no energy element, no inductor is there, and the property of resistor is that until it is getting supply, it will conduct. Otherwise, it will not conduct. Okay, so here D2 was off. Now D1 would conduct for sure, and D2 would be off. Okay, so ideally for this period, D3 should conduct here also or here also. Where I did not write anything, D3 should conduct and not D2 should conduct. Okay. Why? Because a thyristor is not turned on. Okay. And it will not remain on if you say that we cannot turn off the thyristor. It will be turned off because here no energy element and this, this polarity would make this thyristor turn off. This will be in reverse bias. And since there is no energy or no voltage across the resistor after or during 0 to pi by 2, so D2 also cannot conduct. I think it would be more, it become more messy. But what I want to convey here is if the circuit is RL type or any energy or any, RLE, RL type, then this thyristor would continue to conduct after pi. T1 would continue to conduct after pi. But since it is resistive load, so it is voltage a stiff type of load. So if the supply is this, then this voltage across the resistor would be like this. Okay. So after that, from pi to 2 pi, or from pi to 270 degree, no any device will conduct. Okay. Any doubt in this point? Why 0 to pi by 2 or this pi to 3 pi by 2, no any device would conduct? Okay. Actually, ideally, D3 should conducted. D3 should have conducted, but there is no energy. Means after pi, there is no energy. So no conduction of D3 would happen. So that's why RMS value of current through diode D3 would be 0. Because no current is going after 0 to pi by 2 or pi to 3 pi by 2. Am I able to comprehend this concept or should I repeat this?
Sir, please explain it again.
Yeah.
How it is 0?
How it is?
Because D3 is conducting for 0 to pi by 2.
That's the catch here. D3 should conduct from 0 to pi by 2. Okay. But when the energy across this load could be something, right? If it would have stored some energy, then only it can discharge its energy through the freewheeling diode. Okay. The function of freewheeling diode is to uh, discharge the stored energy from any source. So no any energy is stored earlier. So no discharge will happen through D3. So that's why I am saying the current through D3 is 0.
So that means freewheeling diode works only for RL load.
For RL load or for any, RLE load, or if some energy is present there. Because let me draw the waveform of R load, how it happens. Okay, graph. Hmm. Let's say supply is sinusoidal. Okay, this is V in. I should bring back the circuit also. Yeah, so let's see the case of full bridge rectifier. Okay, full bridge rectifier. This is V in. Now, let's assume this diode is not present. Okay, let's say T1 and T2, this consider as T2, and this consider as T3, and this consider as T4. Okay, so from 0 to pi, ideally T1 and T2 would be forward bias. This device and this device would be forward bias from T1 to T2. Okay, sorry, from 0 to pi, T1 and T2 would be forward bias, but it would require some firing angle, and let's say the firing angle is alpha. Okay, so let's say the firing angle is alpha. Now the output is register, so it will follow V naught. V naught would follow after alpha, same to the supply. Okay, now after alpha, sorry, after pi, the work of T1, T2 is done during forward bias. After pi, the T1 and T2 would be reverse bias, and T3 and T4 would be forward bias. T3 and T4. Okay. Now, it would have gone in this manner if there would have some energy stored. Okay. But no energy is stored, and they are in now reverse biased, so no conduction through T1 and T2 would be possible. Now again T3 and T4 would conduct, but alpha is there, pi plus alpha, and again from pi plus alpha it would follow the supply, and this time T3 and T4 would conduct. Okay, here T1 and T2 was conducting, here T3 and T4 will conduct. Okay, any issue till this point? Okay, because it will be repetitive after every pi. It is two pulse converter. Okay, Fine. Now, uh, let's say, and current would also be in similar fashion because I naught is equal to V naught by R. If it is some Vm, it is some Vm by R. That would be I naught. This would be the waveform. Now, what I am saying, during this period, no device is conducting. Why? Because its triggering angle is starting from alpha only. Okay, and in this case, it is D2 or D3. Okay, but it has nothing to conduct. Means resistive current would follow only when this terminal is either positive or negative. If the voltage across this resistor is zero, then you think there is no current. If voltage across this resistor is zero, if VR is zero, then IR is also zero. And if IR is zero, then no current would flow through D3. You got my point? What I am trying to convey here? Yeah, thanks, Anubhav. So I hope you got this point. So this was the basics behind this. If it is resistive load, it will not conduct beyond pi. And in semi-converter also after pi, the conduction is not possible because if means voltage waveform would be same, irrespective of any load. Why? Because the after pi, if any energy element would be there, it would freewheel through this diode. So if freewheeling is going on, voltage is zero, but of course current would be there, some current would be there. So if you know, you can also derive V naught is equal to, since it is repetitive after every pi period, so from alpha to pi, Vm sine omega t d omega t. If you integrate it, you will get Vm by pi 1 minus 1 plus cos alpha, sorry, 1 plus cos. So this expression of output average voltage will be fixed for semi-converter or single phase, what can you say, asymmetric or symmetric semi-converter. In asymmetric, the position of diodes, these diodes will change. Okay, so that's it regarding this lecture. Mm, I hope you enjoyed the lecture. So, any question or anything you want to say? Any doubt or any feedback? Because I'm looking consistently to improve my lecture. So, any feedback you want to give? Anybody? I guess your next class timing is there. So, okay, particular author book for power electronics. Thanks, Kirti. It really meant a lot. Uh, okay. You can refer, you know, Ned Mohan. Ned Mohan is a very, very good book. Ned Mohan, you can refer. I typed in the chat box also. So you can refer and not go for multiple books because you will not get so much time. So always focus what you want to do. You want to understand the concepts and solve the problems. So you should not divert from that. Okay. So, yeah, someone want to say something? Someone mic is on, I guess. Okay, then. So I will wind up the session here. Thanks a lot for joining. So we will meet again next Thursday. Thanks, Sai. Thanks a lot. Okay, fine. So I am winding up the session. I'm still here for a couple of minutes if anyone has anything.